Okay, so this week we're going to talk about TCP IP model and a little bit on hexadecimal because we're going to talk about IPv6. In addition to octal, so we'll touch on the two additional number systems that we might come across when you're configuring network appliances. So a couple weeks ago, we talked about the OSI model, and as you can see, right, on the first part of the notes, it does the comparison. So now in the industry and also in textbook, you're gonna see that some textbook will refer to a 3-layer model, but this particular set of notes gives you the 4-layer model. TCP IP model is just a different model that would represent network communication from bottoms up, just like OSI. It's just OSI have 7 layers and TCP IP model has 4 layers. So when you are going for network plus certification, you need to know your TCP IP models, what are they consist of, and the relevant protocols and services within each of the layer. So at the beginning here, it shows you the comparison between the two. So as you look, right, the network interface is the first layer in the TCP IP model. That will be parallel to 2 layers in the OSI. So when you're getting a signal through a cable that is connected to your network adapter, right, and it started to build your data frame, that is considered to be the network interface in TCP IP model. So you would see 2 layer in OSI that is equivalent to 1 layer in TCP IP model. Then we would have a network layer, which is going to be the same as the network layer in TCP IP. Now, Ethernet, which is 802.3, happens at the first layer in TCP IP model. Then you have IP addressing, just like how it is on the 3rd layer of OSI, which is the 2nd layer of TCP IP model. Address resolution protocol. This particular protocol is used to correlate MAC address to an IP address. This is how your systems are going to be able to be pinpoint on that particular segment. ICMP, this is what we would use for ping, right, to be able to check connection status, or that will be echo and request, or we can use trace route for this, and we'll touch back on this in a little bit. And then internet group protocol, the IGMP is also happening in the network layer. Now, if you're looking at the next layer, which is going to be transport, that's going to be parallel. So you have TCP, in which there has to be an agreement for connection establishment in order to transmit data. And UDP is connectionless. So it's just going to send, when it's available, and it's going to open when it arrives. So UDP is connectionless, and TCP is connection oriented. So both of these protocol happens in the transport layer, which is equivalent on both model. Now you also see ping coming up here on the application, which is on the TCP IP model. That's going to combine session, presentation, and application from the OSI. But ping technically uses ICMP. The reason why it's there is because we use command prompt, right? We use an application to issue that command, which activates the service, right? So it is going to be the top all the way down to the network layer. So ping, dynamic host control protocol, we are going to configure that on our server today, along with HTTP. This is what you would access when you're using your browser. So application layer would consist of application, presentation, and session, and equivalent on the OSI. So let's go through and answer some of these questions. So we can break down the definition for each of the layers. So there are 4 layers in TCP IP model. We would start with the network interface, which consists of physical connection, For example, your network adapter, right, connecting to a cable, or a wireless adapter sending signal to the wireless router, but before it reaches the router, it will be just the wireless adapter. So you would have linking signal in the devices. The second layer in TCP IP model, we mentioned that it is the network, or also known as an internet layer. It's responsible for information delivery after the connection is established, if you're using TCP. But if you are connectionless, right? But anyway, that's gonna be responsible for IP addressing and some of the services for that deals with information delivery. Transport really is the layer that's gonna be responsible for connection establishment. And this is when you see with TCP. So TCP has acknowledgement in connection before it actually transmit data. And so that would be connection oriented. But if you have UDP, it's connectionless. So the session is not gonna be required because it is connectionless. There's no one session for UDP, it's just gonna send in various times. And then the last layer on the TCP IP model is gonna be your application layer, right? Like I said, which is it's combined the three top layers from OSI. It's gonna be responsible for network requests from the source to the destination. And it's mostly deal with application and translation from the application to the data content delivery. So for our final exam and our quiz, make sure you know these 4 layers. For the certification, you also need to know these 4 layers for TCP IP model. Now, to kind of include some of the example, right, or identify some of the protocols and the services for these layers, you can refer to number 2 or the part 1 of the notes, page 1. So if we're looking at the first layer, you would see that it is Ethernet 802.3, which is when you have adapter connecting to the cable. And then your Wi-Fi connection, which is 802.11 in different standards, right? Currently, we're using AC. And then the next layer is going to be your network or internet layer. And if you look at the image on the first page, you would see there's IP that's mostly used, it's used for addressing only. ICMP, right? This is going to allow us to be able to identify connection status for different systems. ARP, which is Address Resolution Protocol, and IGMP. Now, if we are looking at, like, for example, traceroute, right? I showed this to the Friday class. So if you open up your command prompt and if you type trace RT, and what we can do is we can just say google.com. You don't need the www before that because the command doesn't understand that. So in Windows, when you use traceroute, it uses ICMP, and it sends the echo to the system that's receiving that packet. So basically, we're following the traffic from my computer to Google server, right? And you can put in any domain that is publicly known, right? So, and this is what you see at the internet or the network layer, is that it's going to correlate, the DNS handles the domain name association with the public IP. So technically, the IP address for the web server for google.com is that IP. And as you can see, it's IPv4. And so when we look at that, we would see that the first hop is gonna be the router, right? So from my computer, it needs to go to the gateway that I am closest to, which is a .1. That's what you see here, right? And RCCD has another router that's going to be a .5 here. Because I'm using the wireless network, it's going to pass it into this gateway and then another router here. Now you notice that the traffic is going to be slower than what we would normally see when we just type in the URL through the application layer, right? So what you see is you are going to see that it's actually communicating with the receiving system and then report back, okay? And then sometime if it's not able to obtain the information, it will be timing out. And eventually it will list all the hop, which are the routers that are receiving my traffic. It's kind of like putting a camera on your car, right? And then taking your car from your home to your work, and we would see every street and corner that your car turned, right? Or navigate to on the way from home to work. So this is what you would see. It is taking a little bit longer than it is expected, but this is what you would see with ICMP, and this is the same thing with ping. Let me cancel that. And so, yeah, sometime I have to give it a little bit. So when you start seeing the 205 right there, that's when we start entering into the vendor, which is your ISP. And then anything that's cynic.net, that's the RCCD service, internet service provider. So you would see that their routers are located there, and it would show you the IP address. And you can see that it is passing into this domain, right? So you can see a lot of the system, it has the IP address in it. It's going to forward that. And then it's going to go into some of the public systems. So the automated system, so what autonomous router system, and then eventually it's going to get to Google in the LA location. It's going to show that. Yeah, today is a little slower than usual. So, all right. So this is what you see, right? So when I type in google.com, because of my regional location, right, I would actually visit the closest server, which is from the LA data center. That's what you see here for Google, and that's the IP address, okay? So IP address plays a really important role. This is why it's called the internet layers, because that's how we can interconnect with the systems that are outside of our local area network. Now, Microsoft command prompt is only going to give you sometime a summary. So you are going to see like maybe less than 10 hops or less than 30 hops. Usually it lists less than 10 hops. So the main routers that reporting the traffic back to your system, right? However, if you are actually following it, it sometimes goes over 10 or more, or even above 30 hops, depending on the location of the server. Okay, so we talked about the IP, the ICMP, address resolution protocol. So next week, when we look over the utilities, right, we're going to look at our table. I know some of you are taking 27. CIS-27 talks about like ARP, how ARP plays an important role in the security and how it has vulnerability. And then you have transport, TCP, UDP. We touch on connection and connection-less oriented. And then the application, HTTP and HTTPS, this is what we see with our browser, which is an application. And then telnet is a way that we can have system directly communicate and send plain text, right? Unencrypted messages to one another. So for example, if I need to connect my laptop to a switch or a router, I have two options. Number one, I can use telnet, which is not secure, right? And we talked about the port for this. Number two, we can use encryption and directly connect, so I can configure using SSH. And you can do the same thing if you connect to a Raspberry Pi or another system. And then your network time protocol, your NTP. This is used for synchronization across the network with different systems. More on the user side, this is what you see with daylight saving on how you just connect to a network and it updates your time. Okay, so you can look at the first page of your notes for all of this information, very easy to find. Okay, so before we get to the flags and the information here, I want to bring you back to the notes, right? There are additional protocol that we don't really mention in our assignments, but it's important to kind of think about, right? So I already talked about SSH, which uses encryption for direct connection. The PPTP and L2TP, we will see this later when we configure remote access server role. This is often, and IPsec is used for remote connection and IPsec is used for VPN. So if you configure a VPN server for your network, right, preferably we want to use IPsec and then PP point-to-point protocol. This allows the system to connect to multiple points remotely. And so it talks about how there are some security protocols that will work directly to some of the layers that you would see in TCP/IP. Okay, so read more about each of the layers' functionality. And here are the TCP flags. As you know, TCP needs confirmation. It's kind of like sending a package to someone that you know, but you require a signature for that package, right? So the delivery person has to knock on the door, identify the individual that receives the package, make sure that person signs, and then hand them the package. TCP works that way. It makes sure that there is a communication point from one system to another, so there has to be an acknowledgement. And in order to synchronize and transmit data, the two systems has to agree that data will be transmitted. Once it's done, it's going to finish out by doing a thin flag. So how does it play into a TCP header? And those of you who are into security tools, you're gonna see this is gonna make sense when you look at that, right? So these are the components of the TCP header. Because TCP require confirmation, you're gonna see that there are a lot of different components. So there are 32 bits, of course, for the packet. You have the source port and the destination port. So last week when we did Wireshark, you see that this is how Wireshark pulled the information is from the header. Think of the header is like the label on your package that you send, right? It would say who's sending and who's receiving that package, right? Your address information, the weight of your package, and the same thing, this is like a form of label for the packet, which contains data that's transmitting between the system. So it's gonna say the source port, we looked at this on Wireshark, right? The destination port, and the source port could be dynamic port or it could be a well-known port. The destination port tends to be a well-known port like port 80 or port 53, depending on the protocols that you use. Sequence number is important. Kind of like how you send multiple packages to your friend, right? Package 1, package 2, package 3. And you tell your friend that when you receive all 3 packages, open them in order. And that's what TCP does, right? It has to make sure that it checks the sequence so that way it can reassemble your data because packets arrive at different times. So I might receive the 3rd one before the 2nd one, but because of the sequence number, you're at the application layer when you're trying to load a website or the content, what that does is it's going to make sure that everything is in sequence, multiple packets, it's going to be able to provide that for you. And then it has the acknowledgement number, which is like a confirmation number. Now, these flags that we're talking about on the next question, they take up these bits, okay, in the header itself. And there are also the length, which is how big is your header, that usually contained in the 4 bits. And then there are some reserved bits, which is 6. Now, if you have an urgent flag, which means it's priority, it's kind of like sending a priority package to your friend, that's going to initiate the urgent pointer. If you know programming, pointer is just an address location that points to, right, the information for that particular flag. So the urgent pointer here, right, and then the checksum, just making sure that we look at the entire content. So it verifies that everything is intact. And then there's some option bytes, but your payload, right, is usually down here. And we saw this when we look at Wireshark, like it could be 394 bytes, right? It depends on your frame. If it's a normal frame or is it jumbo frame for your packet. So now when you're using security tools or network monitoring tool, it usually refers to header information to give you the output that you see. So when you're scanning ports or scanning vulnerability, where is that information coming from? Usually it's coming from your traffic information, just the label for that packets or your header, right? All right, so let's talk about these flags that you see are right here. Okay, so first we're going to talk about SYN or synchronization. SYN flag is assigned to any packets that are part of the synchronization space in the three-way handshake, right? When we looked at when we followed the stream for our traffic last week, you saw that the HTTP traffic that you generated, it had SYN ACK, right? SYN ACK traffic. So with that, for that particular packet, that bit is turned on for SYN. That means that it's established the communication and it's synchronizing. Okay, and that's how you're able to do a GET task on HTTP or through your application to load your website. So this is a sign when there is a three-way handshake. There's agreement for communication exchange. ACK stands for acknowledgement flag. This is when it receives information, right? And there's a confirmation. It's kind of like how you sign for your package when they deliver that, right? Your signature verify that, acknowledge that you received, right? So the receiving system at that port, it's going to have an acknowledgement flag. So this bit is going to be turned on. Then you have a PSH, which is a push flag. And this is a way that we can force the data on an application. This doesn't happen very commonly, right? But in the case where, for example, if you're stuffing data or crafting packets, sometimes that you have to modify the flag. So the flag is designed to force the data onto an application like your browser and so on. So when you see this and it's not intended, so let's say that two systems is just communicating, but if the push flag is on, sometimes that could be a sign of something that's irregular. So you want to be able to look at that. Urgent flag, I talked about that already. This is priority, right? It needs to be sent or received immediately. And then fin is just a finish flag. So that means that it's going to terminate the communication up on that flag, right? So once it turns on that bit, the termination is completed. So communication is terminated. That's it, right? So communication is done, finalized here. This is what you see with fin. And then RST is a reset. This is usually, sometimes you would see an error, or like you know, on Wireshark you see like maybe a black or a red packet coming through. And the reset flag is when it ends the TCP conversation by just hanging up. So if it terminates early, there is maybe a disruption in communication. When it's submit a reset flag, what that does is it reactivates that. So it is a way for the system to know to resubmit. So it goes through the process of resending again, so that way your data will get from point A to point B without losing the data to begin with, right? So all of this information, again, you can find on our notes, but make sure you understand each of the flags. So it makes more sense when you're looking at Wireshark, right? Or Network Sniffer, and you see these flags. Now, some application like Wireshark, it would show that through different menu option. You have to turn that on, like we would have to follow the stream. With that option, we will be able to see it, but in the normal packet, you would not see it, right? Any question? So again, right, you can come back to page 2 and all of that, you can find that here. And then you can check out the image for TCP header. Below that, it will tell you each of the components, what that means, the size of it. I don't need you to necessarily memorize like the bit size, but know what it's supposed to do. Because when you obtain information through your network monitoring application, right, you have to interpret that. So for network analysts, engineer, security analysts, we have to take the information and interpret it. So making sure that you understand what this means, right, is important. Okay. So let's compare that to a UDP header. Remember, UDP is kind of like, you sending your package with the lowest rate, and if it arrives like 15 days later, that's fine, right? Or a month later, that's fine. And it's kind of like they just throw it at the door and leave, right? So UDP doesn't have too many components. It's much simpler. So there it is, right? Which is kind of nice, short and sweet. You have where it's coming from, where it's going to, how long, and it does a checksum, right? So UDP header, when you're running a tool that analyzes UDP, it's gonna tell you just very simple information because its header is very simple. Okay, there's no additional flags or anything. Like I said, right, it arrives sooner or later. Okay, so let me move this up in case you're still recording the previous question. So the 4 fields for UDP, you have your source port, which is 16-bit. It indicates the door or window, right? The port where your application is used to send. The destination port, which is also 16-bit. Remember, these things combine to be 32, right? Indicates the port that's used to receive. It's kind of like, how you open the door to receive your package, right? You open the door to send your package. So these are send, receive, right? The length is also 16-bit. This is going to specify the size of your header in bytes. And then your checksum is also 16-bit. This is to make sure that there is integrity or entirety of your packet is received and sent. So checksum. So every protocol that you see, right, TCP, UDP, IP, Internet Protocol, has header. Like I said, it's a way that we label the traffic, how it's sent and received, and the type of services that we use with that packet on the network. So that way the system can distinguish, right, what they are. Any question? Okay, so now we're going to touch on IP. And Internet Protocol is specifically for addressing and routing. So we use IP addresses for the router, right? The switch, unless it's multi-layer switch like layer 4 and up, then it would use IP address, but the lower switch, that's your simple even managed switch, only use MAC address. So your IP address, public IP, we know that that's used in the larger global aspect, where private IP we would use inside the network, and we talked about that before. So we mostly use IP address so that way the router would know, right, which network that's coming from. So that's just like kind of like saying that if you travel to another country, you show your passport and they would know that you're from the United States, right? So that would just means that if I'm using a specific assigned IP address from my internet service provider, they would know that I would be transmitting from this particular network through my router, okay? Now, we don't want system to hang on to communication too long, especially if things are not respond in the way that we want. So your TTL here, your time to live, it would be used to make sure that things get there in a timely manner, right? So there's a window of time that's allowed for the packet to get routed, okay? Now, all your router, we're going to have a unit on the router. Your router, depending on the service that you use, right, the manufacturer, the protocol, what it does is it's going to determine, right, like which router is available by checking, okay? And it's going to make sure that this window is met. You saw earlier when we do trace route, right? Sometimes it would take a certain amount of time to pass from one router to the next. But when you submit a packet or you send a packet and it gets routed, it's going to increase that bit that was on to 0. So it drops that. And once that happens, it's going to remove that and send the status to the sender. So you saw this with trace route, right? You saw that I have 4 milliseconds and it reports back to me that this router handled my packet. And then the next router picks that up and it reports to me again. So let's look at that again. I have it open. Right? You see this here. This is what it's referring to. So the time to live really talks about these columns, that how much time can the packet gets passed from one router to the next. It's kind of like, you know, if you go through that street and Google Maps tell you that you should take 2 minutes to get through that street because there's no traffic, right? So ideally, it's the time window that we can go from one street to the next street and so on. So basically, this is going to be the TTL. As the router passes it through and it reports the information, it's going to turn off that bit to 0, right? As the next router pick it up, right? So your TTL is shown there. Okay, so it specifies when that time is up is going to be the time to live, right? There's a maximum number of milliseconds that it would use to get the packet to a certain location. And when it reached that maximum value, right, that's the expiration. And this is how we can make sure that things get from one place to another in a timely manner, okay? So in the IP header, this is the most important area. Any question? Okay, so if you need reference for that, you can go to page 3. right? If you're working on the last section, you can go to the previous page for the flag information and the header information. And when you look at the image for the IP header, it looks like this. It is a little bit more than your UDP. The TTL is right here, right? There's your protocol, your source and destination address. Remember, right? This is going to be the IP. So it will be your IP addresses versus your port. Now, on the IP, you notice at the top, there's a version, right? We've been talking about version 4, which is what you saw when I did the trace route. But if you're using a version 6, that value is going to be indicated at the top. And then there's a fragment offset. So as you would know, right, it would not be contiguous. It would not be together concurrently all the time. Information is going to arrive and it's communicated in different time and different sets. So what you're going to see is you have these fragment offset value, which is going to be indicated kind of like a flag. So those are the bits that it needs to be activated. And then just like all the other headers, most of the other headers have checksums. So we want to make sure that there's entirety of the communication. So these are your flags, right? And it talks about that here. So the fragments are going to be indicating if there are fragments to come, bits and pieces. If there's multiple fragments, if there isn't, then it would have the 0 turns on, but usually you would see some fragments. And then the offsets, it's just going to be an allocated value that it would deal with the fragments. So I give you the breakdown for each of the component for the header. Any question regarding IP? We'll talk a little bit more about version 6 today, but what you see with a lot of the example when we looked at addresses, many networks still using version 4. Okay, so we're gonna use ICMP, and you saw this with traceroute, right? Another way that you would see with the ping command or through the app is if you do a ping, right? So for example, if you saw the loop back last time, right? Yeah, sure. Yes. Packets are always out of sequence. So it's kind of like you go to the post office and you bring 5 packages there. You tell them that you want to send these packages, right? They don't necessarily arrive at the same time, right? So your package 5 might be coming first, and then the third one and the second one. But TCP, it waits till everybody gets there, put them all back in order, and then present it to you. But UDP is going to open the 5th one first, and then the 3rd one, and then whichever arrives is going to open that one. This is why what you see is it's still buffering when you're watching your video, because you might have data that's earlier or later arriving in different time. Your data is never ever in contiguous. It's always fragmented. Okay, so when we do a ping command, right, this is through an application layer, but it still uses ICMP service. So basically it sends, in Windows, it sends 4 requests, 4 replies. We saw this last time, right? Now, if you are trying to ping a system that doesn't exist, right, you might have a timeout, remember, right? There is a time to live for these requests to be submitted. If it's not received in a certain time, the maximum time is reached, it's going to drop it, and it's going to report back to you. It says unreachable, right? So that way you know that that system is not connected. We mostly use ping and traceroute for connection status, okay? So Before we answer that, let's look at this. So ICMP, Internet Control Message Protocol, this is to use status and error updates for your system. Okay. So you often see that when we're using ping, when you submit ping and an IP address command, right? Like I say ping 127.0.0.1, then what you would see is you sending a forward request, and the receiving system is going to send echo back. So when you run Wireshark while you ping, you should see these packets coming through as request and echo as ICMP. You can try it, right? So if someone is pinging you, if they're doing a Smurf attack, you're gonna see, because your system is always, if it's enabled, it's going to reply, right? The way that they do the now service with ICMP is it's gonna drop thousands of requests at once. And then it bogs down your system because now your system is too busy responding back. And that's how they can do a Smurf attack, right? So you can, it's really created so that way it would respond to the number of requests that is submitted for the status. And then your trace route, now if you're using trace route in Linux, you have to spell it out, trace, R-O-U-T, right? Versus in Windows, you just do a trace RT. So we'll talk about utility next week. Okay, just know that ICMP does not use port number, right? And so it uses types and code to really identify different messages. So when you're doing a ping, right, it's a different message that is coded through a ping command compared to a trace route where it knows it's coded to report back with the hops, right? So that is a little bit different than some of the other protocol. And so if you're looking at the type and code, you can see that on the below table. So if I do a ping, right, and you saw the reply from my ping, it uses the code 0 and your ICMP type is 0, right? But if I ping a system that is off or it's not reachable or it doesn't exist, it's gonna be type 3 and then the code 0. So based on the type and the code, it would be able to report to you whether the host is replying, reachable, unreachable, right? Destination is unknown, etc. And that's how it's able to show you that on your application like this. Okay, see? So that's how we get this answer. So what is used for ICMP to identify different types of messages, your codes, and your type, and you can refer to that table on your notes. Any question? So it's gonna start becoming clear. I really feel that most of the time students should take networking class before they take security classes, because it's gonna make a lot more sense on the things that you see and the things that you do through the security tools. So for those of you who are taking my 41A in the next semester, right, in spring, right, you're gonna see some of these vulnerability tools and the things that you use. You're gonna be like, right? I hope that you go back into your knowledge and you would say, oh, okay, I remember that I learned about this, right? Just like how we talked about ports and we looked at it on the Wireshark, it makes more sense when you can apply the concept and you see it, right? Any question? Okay. All right, let's bring 6 down and let's talk about the next topic. We have to get through some of the. Okay, so now, with all of that said, we're gonna turn right and we're gonna go into IPv6. Okay, so let's talk about IPv6 before we answer that, okay? Oh, I forgot to show you this. ICMP header, the code, right, 8 bits, the type 8 bits, and then your checksum takes up
combined 16 bits. Again, it has to have a sequence number, right? Identifier. It uses component like magic number, but it uses IP because ICMP is part of the network layer. There is a field for port, but most of the time we don't really use port for ICMP. We care more about state, right? And then your length for your header, acknowledgement number, because it is part of TCP suite. And then your sequence number, so that way you can put things back in order. And then your payload is at the bottom. Sometimes you don't have payload, so your data is optional here. Okay, and then it talks about a different protocol here. So address resolution protocol, I touched slightly on this at the beginning. It is a way that we correlate IP address to a MAC address. If you do like ARP-A, that's going to give you the table for your connected systems, right? So we'll look at the utility next week. ARP is very important in security as well, because someone, if they have access to your ARP table, they can, usually for spoofing purposes or modifying address and MAC address correlated information, because it's stored, it's caching to your system, right? If they want to be able to spoof or hide their identity, they have to go in and modify the information in the cache. Okay, so IPv6, the reason why it came about was because publicly we ran out of IPv4 in 2011. 15 years later, we're still using IPv4. There are many companies that have a large amount of IPv4, like Microsoft, cloud companies. But as you are using more IoT devices, smart devices, you would see that IPv6 is required, right? So that way, we will be able to have enough addresses because it is 128 bits. So if you take 2 to the power of 128, it is much larger in size than 2 to the exponent of 32. So also, when they designed IPv6, they looked at the flaws from IPv4 and they said, okay, we have to make a system that is more dynamic, that is going to be able to automate a lot of the things, because we don't want to have to manually create or configure, the addresses, so that way it's going to not have any conflict. So you have larger address space, and it can be used for multicasting purposes. IPv4, there is an option for us to do multicast, and we talked about that last time. But there is a specific area for IPv6 that's going to use for multicast, which is going to be more efficiently handled instead of doing it as a broadcast. And then IPsec, it specifically can be used with version 6, right? Because if you say IP security, that's version 4. And then if you use version 6, there is a version 6 that supports it. So you can implement that for your virtual private network configuration with tunneling. Okay, so you are going to use hexadecimal number today. We are going to, do a little bit of converting for the hexadecimal. So let's take a look at the highlighted address, right? It is a hexadecimal number, right? 0 through 9, A through F. And you are going to use the colon, right, to separate your blocks. So you have 16 bits each for the block. Now, each of your hex character, for example, the first digit is a 6 right here. That takes up 4 bits, right? So if I take 4 plus 4 plus 4 plus 4, or 4 times 4, I have 16 bits. So each of your block separated by a colon is going to be 16 bits. And combined, the entire address takes up 128 bits. So it's much longer. Now you notice in the middle, you see a bunch of zeros here. So you have 2 blocks that are all zeros, right? This middle part. Now, the way that we can shorthand it, we can condense it by using a double colon. Double colon is going to condense that. So whenever you see that, you know that that is represented by the blocks that contain only 0. Okay? Or we can also condense it by a 0 and a colon. So now the reason why I show you this is you are going to see, right? Some systems, it's going to have the double colon. And some system, the way that they manufacture it, it's going to have a 0 and a colon. You need to know what that means, okay? Because just know that it is a block that has zeros, right? The 4-0, and it's just shorthanded. So in this case, instead of writing out a bunch of 0 like this, and then a 1 at the end, that one is significant, right? We can just shorten it by the 0 and the colon and a 1, or we can use a double colon, right? And then the last block, okay? So to answer the next question, you have 3 types of IP version 6. Unicast, this is used for one-to-one system. So if you have one-to-one system communication only, you're gonna do a unicast address. Then you have a multicast address. This is used to send to a group of systems at one time. So multicast address, often you're gonna see it's gonna show FF. Usually when we see an F, that usually indicated either a broadcast or a multicast. But you see a prefix FF01, that's an indicator for a multicast. Like this, FF01, and then you see a double colon, what did I say? That's a bunch of zeros, 2 blocks of 0, and then a 1 at the end. So a multicast address, it might look like this, okay? FF01 double colon 1. And then so that means that it's going to send to all nodes for that group, while if you use FF01 double colon 2, this is going to send to all the routers on the network. So we can use it to be able to communicate with all the appliances that will be connected, specifically like the routers, using the multicast address. Okay? And then any cast is like the broadcast. It's going to be to all, right? But they don't name it as broadcast because that can be misleading, right? Any cast is going to be to a system, to a group of system for the service. So for the next question, you can go to that page. We have unicast, multicast, and anycast for the type of IPv6. Now, in the unicast, you have 3 categories. One is going to be a global unicast. This is your public address, that's version 6, that's used worldwide, global, right? Your site local unicast, this is like your private IP address that's used inside your LAN. So if you're looking at, if you type in ipconfig and you see a site local address, that means that it is a private address to the network that you're using. Then your link local unicast is used for linking only. Now, if they're not using IPv6, you would see that this is omitted from your configuration information. This will probably not be included. You might have a link local. You see this with Kali Linux when you pull up the information from Kali. Sometimes you see a link local. Any question? Okay, so for final and quiz, make sure we know the types of IPv6 address, right? And then the type of unicast address, that's version 6. Any question? Okay, so before we do the next exercise, we need to look at this table, right? So this is a hexadecimal system. So when do you see hexadecimal? You see it in memory addresses and system addresses, right? Like IPv6. You see this in MAC addresses. You see this in when you do HTML and you are using the color wheel, right? You see the hex value for color codes when you're programming HTML. So hexadecimal is very commonly used in a lot of areas, more than we know, right? So hexadecimal 0 through 9 is equivalent to decimal, right? 0 through 9. So if you have a 0 in hexadecimal, it is a 0 in decimal. And decimal is the number system that we count. Lastly, when we did the conversion to binary, when we're going from decimal to binary, we subtract, right? And vice versa. Now, we are going to use the same approach today, but in hexadecimal, when you get a decimal that is a 10, your hex is an A. When you get a decimal that's 11, it's a B in hex. So after 9, you're going to have A, B, C, D, and F is going to be the last one. Okay? Which gives you 15 in decimal. So that gives us 0 through 9, A through F. That gives you 16 number in the system. Notice that the F is when all the bits are on. So each of the hexadecimal character is equivalent to a nibble or 4 bits. It's always going to be 4 bits. Okay? So if you have 2 characters, that's 8 bits, right? You saw earlier a block in an IPv6. 4 characters, that gives you 16 bits. So 4 bits per hexadecimal digit. Okay, with that said, let's do some conversion. Okay, so I'm going to start with the number 2 on the most left, right? We know that a 2 is a 2 in decimal, okay? You are going to use the same scale, 1, 2, 4, and 8, okay? Remember, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Why do I stop there? Because there's only 4 bits, right? The placement is going to be my bit 1, bit 2, bit 3, and bit 4. Okay, so only 4 bits in a hex. So I look at that scale and I said, which number represents the 2? Well, the second bit is going to be the 2, right? I can subtract 2 from 2, so I put a 1 underneath, and the rest is on. So my 2 is equal to 0, 0, 1, 0. And you can also use the table that I gave you. And then I do the same thing with the next digit, which is the 6. So a 6, you ask yourself what numbers add up to be 6? A 2 and a 4, right? A 2 and a 4 gives me a 6. So the second bit is on and the third bit is on, and you put 0 for the other bits. Okay, that gives me a 6 because a 6 in hex is a 6 in decimal. And then the easier one is the 0. So whenever I get a 0, everything is 0, right? So you just put 0. Okay, so if you want to make the table and draw the table like I did, right, you can do insert table and then click draw table. And then you just select the number of columns and rows that you want to draw your table. But you can use insert table. And then here I would put like 5 columns so I can label and then 2 rows. So if that helps you, but you don't have to. So as you look at the scale, it's always going to be multiple of 2, and it's the same. You ask yourself, what number can I add up or can I select to represent that value, right? the 0 is not on the scale, so everything is off, right? Everything is 0 on the bottom. Okay, let's take a look at the last digit, which is a 3. So I asked myself on this scale what numbers I can add up to be 3. I know that a 1 plus a 2 is 3. So those are the bits that are on. And 4 and 8 is too big. 2, it's higher than 3. So I will put a 0, right? So that will be 0, 0, 1, 1. Now you can use your programmer calculator. I only do this so you can visibly see, right, how I derive that value manually. So if you put in your calculator, again, I'm going to do this in case you missed that part last week. You open up your calculator. I have it on a scientific mode. I click the menu option on the top left or open navigation. I select programmer. Now I need to go from hex to binary. So I simply select the hex value, right? So I would put in 8 and then I would get the binary like this for the one in yellow, right? So you can use your programmer calculator to derive those. So, you don't have to do the entire thing, but if you want, like me, you would have like this. Okay. So I'll do the next one with you. Okay, so ultimately, when we write out that addresses in binary or what the system sees, the hex address, right, it converts that into binary and it will look like this, right? And more.
Question,
Sure.
on the fifth set, it's just 96 E's, what, should there be a fourth digit somewhere, or is it a ending 0?
It's an ending 0, or it's a starting 0. That one.
Oh, it's
A starting 0.
Oh, it's starting 0.
Yeah, 0 before 9. So it's that doesn't. Yeah, so sometimes you're gonna see that when you type 0 into the calculator, it's not gonna mean anything because that bit is off. So, or the 4 bits is off. Yeah, it's 096E. Okay, question. Thank you for asking that. Okay, so let's do the next one. So I'm gonna do FA40 for you because when you get to the letter, it gets a little harder, right? So we know that when you see a letter F, all the bits are on because if you take the decimal equivalent, you add it, it equals to 15. So if I take 1 plus 2 is 3, right? Plus 4 is 7, 7 plus 8 is 15. That means that if I need 15, all of my 4 bits would have the 1. That means that all the binary is going to be 1. So F is going to always be 15 in decimal, and it's going to be all 1s in binary. Now, if you see, like I said, if you're looking at a broadcast address in hex value, you're going to see that it's going to show F, right? Just like how you would see 255, right? All the bits are on. And then for the next character, which is an A here, an A is a 10 in decimal, right? And that would be what adds up to be a 10, a 2, and an 8, right? I take 2 plus 8 gives me a 10. So it's on here, and it's on here, and 0 and 0. And then for the 4, that one is easy. It's on the 3rd bit. Everything else is off. So 0, 1, 0, 0. And then when you have the 0 for the last one, that's going to be all 0. So that's how I got the blue highlighted thing. Okay, so the takeaway from this, always remember that hexadecimal is gonna be equal to 4 binary bits, okay? You get 0 through 9, that's gonna be equivalent to 0 through 9 in decimal. And then when you get 10 through 15 in decimal, that's gonna be A through F in hexadecimal. And when you're going from decimal or hexadecimal to binary, you do the subtraction method like what you've done last week. Now we're gonna go in reverse. Any question with this before we go to the next part? Okay. So we're given these binary values and we need to convert it to hexadecimal. The easiest way is to chunk them up into 4 bits each. That represents each digit in hexadecimal. I already typed that out for you in increments of 4, right? And I highlighted them so that way I can show you my work. So you already did this one up there, right? So you know that this is equal to an F when you have 4 ones, right? So let me move this down real quick. Okay. So to start with the yellow, I'm gonna start with 4 ones right here. So I would take 1. Oh, I should start with the left. I would take 8. That's the first one, plus 4, that's the second one, plus 2, that's the third one, plus 1, that's the fourth one. And I add everything up, gives me 15 in decimal, which gives me F in hexadecimal. Okay? So when we're going in reverse, we are going to add up all the values. So when you go from binary to hexadecimal, you're going to do addition. Okay? Now, next is going to be the green. Which is these 4 bits right here. The next one, the next chunk. I have 1101. So let's put it in the table. Let me undo the highlight real quick to not confuse you. Okay, so you're gonna put 1101 into the table. And you would add up the values. So I'm gonna add up 8 plus 4 plus 1, which gives me 13, right? So you can just use one table and then you just interchange or change the value as you go. So 8, which is the first one, plus 4, right? Second one, skip this one because it's 0, and then add the last value, which is 1. So I have 13 in decimal, and 13, A, B, C, D, right? So A is 10, 11 is B, 12 is C, and D is 13. So 13 in decimal is going to give me D in hexadecimal. Then next, I'm going to do the blue. And again, I'm going to plug in the value. So let's change this up to the given value. So I have 1001. And I would only add the value that has the 1 at the top. I mean, the 1 at the bottom. So I take 8 plus 1 gives me a 9. A 9 in decimal is a 9 in hexadecimal. And as you go, it's really easy, right? Because there's only 4 bits. So you ask which one, right? I already know 1, 2, and 8, right? So 8, 2, 1 gives me 11. So let's do the next one in pink. So we have 1011. Sorry, my mouse got stuck. Okay, And for the 1011, I would take the 8 plus the 2 plus the 1, which gives me 11, and 11 in decimal is a B in hexadecimal. So all of these combined is FG96 with a base 16. That is quickly part of my address, right? So that's how we convert. Okay. Now on the next one, I only did one part, one digit, and so you can do the rest, but I think I wrote down the answer. But when you look at the placement of the bits, you can just quickly do it in your head. It gets easier when you practice, right? So here, I know it's if I put it on the table like this, I have 100 for question 10B for the first part right here, which gives me an 8 because only that bit is on. The rest is off. So this one represents an 8. And then this one, if you look, right, 1, 2, 4, 8. So 2 plus 4, that gives me a 6. 1, 2, 4, 8. So 2 and 8, that gives me a 10, which is an A. 1, 2, 4, 8. 1 and 2, that gives me a 3. Yeah. And the previous question? So the F, right? If you put the F in, there are all ones like this, right? So that means that I add all of these up because they are all on for the F. For the yellow, how do I know what? Okay, so it is a scale. So in the hexadecimal system, coming back to this table, right? An F is equal to your number 15. So if you have a sum of all the value is 15, that's an F. If you have a sum of all your value added, that's 13, that's a D. So when you add it up, anything above 9, you have to ask yourself, what is 13 in hexadecimal? What is 12 in hexadecimal? So this is just a system that they use, right? Yes. So just know that A through F is equivalent to 10 through 15 in your decimal. You see? Hexadecimal A through F and decimal 15 is F. Okay. See, I did not solve, so how do I put this in the calculator to do it quickly? Because maybe it's hard for me to memorize, right? For C, you open up your programmer calculator, click bin, and you just type it in 0010, right? Like this, and you click the hex, and it tells you it's a 2 in hex. And then you click clear, so that this is equal to a 2 right here, right, in hex. And then the next one, you punch it in your calculator, right? Select bin, and you type 1010, and then your hex, that's going to be a 10. But you can also manually do it, because sometimes when I manually do it might be quicker. I just add the value up, and I could see what the sum would be. So 2, 4, 8, right? Bless you. That's 14. What is 14? Going back to what Dima was asking, look at the table. What is 14 in decimal? That is equal in hexadecimal, right? Okay, so once you have each of the digit, you write it out as your answer. Okay, any questions with hexadecimal? So you don't have to do addition and subtraction and multiplication in hex. But my assembly class, they have to know how to do that because they need to program at low levels, so they need to know what the computer sees at each address, right? So. But computer science students, they have to know that. So at least we can look at the hexadecimal value in an IPv6 and we know what it represents in binary. That's my point. Okay, let's talk about octal. Okay, so we talked about hexadecimal. Each digit is 4 bits. Okay, octal is used in an older system. You guys ever play like low bit games? Right? I'm sure you do, like the retro games. Okay. Those are because the bit size were a lot less because the processor can only handle lower bit size. Now we have more advanced processor that handles 64 bits. But back in the day, we started with 8 bits, even lower, 6 bits, right? So you have 8 bits and then eventually 16 bits. This is when you start to see like Windows 98, and then you have 32 bits, which is where XP era, and then Windows 7, and then eventually you have processors that are 64 bits, which is what you're using now. So octal value is used on mostly older systems. The reason why I show you this is you might come across older appliances where you see octal value. Similar to hexadecimal, right? Same technique that you see in conversion, but octal, they're only 3 bits. Hex, 4 bits. Octal, 3 bits, right? So, and when you see the octal number, it is indicated with a base 8, like this. Okay, so the next question, 11A, you have 2, 4 octal value, right? How do I convert that? I would start with the number 2, okay? So let's do that first. Let me clear this. So I use the same scale. It's multiple of 2. Why? Because it's binary that we're converting to, right? This computer knows binary. That's it. 1 times 2 is 2, times 2 is 4. We stop there. Because in an octal system, there are only 3 bits per digit. So the digit 2 here, it's represented in 3 bits. Okay? So which bit is on? I subtract, I take the number 2, which is my first character here. So let's start with the green, right? I would then ask myself, can I subtract 4? No, put a 0. Sorry, let's change the highlight. Can I subtract 2? Yes, put a 1. So 2 subtract 2, I have nothing left, right? I have a 0 right now, no remainder. So I cannot subtract 1, I put a 0. Right? So subtraction method, just like what you did in the last one. So the 2 represents 0, 1, 0. You see that? 0, 1, 0. And then the 4, really easy. So let's use this as blue. So if I'm going to clear this table out again so I can do this with you. So 4, which number I can subtract? I can subtract a 4, put yes, put 1. That bit is on. And as I subtract, I have nothing left. So I put a 0 and a 0, right? And so therefore, a 4 in octal equals to a 100 in binary. And you can use octal in your calculator by selecting OCT. So if I put in 2, 4 in octal, remember I have to select it first, right? Type in 2, 4 and I click bin and there I have it. But you're like, wait, where is all this other 0 coming from? Well, the reason why is your calculator is designed to give you a certain bit size, right? So if you condense and drop some of the zero in the front, you would have it. Like if I omit the first two zero because it's less, right? Then if I remove the first two zero, you would have the actual value. So it does look a little confusing because it's meant to give you, because I have selected a quad word, right? A word is 16, 4 times 16 is a 64-bit result. So you can also shift and change your word size here. You can modify this right here. A D word, etc. So it actually changed how you represent your result. But that's how you can calculate output. Yes.
That base.
Okay. So the base is just telling you the number system that we use, right? The little a indicates that it's an octal number. Okay. Yeah, so an octal number 0 through 7 is equal to 0 through 7 in your counting number, your decimal. Okay. So if you recall last week when we did the binary conversion, so I'm gonna clear this out real quick. Right? You did a subtraction method, correct? So looking on this scale, and this scale stays the same always because it's multiple of 2, right? Why is it 2? Because binary is 2, base 2. I shouldn't say base 2. Binary is multiple of 2, okay? Because that confused you, okay? So I asked myself, which number can I subtract from that? Can I take 2 and subtract, right? I can't subtract 4 because it's larger, right? It will go into the negative. 2 minus 4, I cannot, right? I have 2 eggs, right? And I want, right? And I'm trying to use 2 eggs only, but now here it says that it has 4. I cannot subtract that. So 2 is smaller than 4. So when you have a smaller number here, you put a 0. So I cannot subtract a 4. So put a 0. Okay. Okay. So Dima, in the last one, that's a hexadecimal number. Different number system. Okay. In this one, it's an octal number. So octal number has 3 bits. You see the bit position? In a hexadecimal, 4 bits. So a hexadecimal number is larger than an octal number. Okay. So it's kind of like different counting number, as you can say, for the computer. Okay. The computer used binary, octal, hexadecimal, and decimal. But ultimately, all of these hexadecimal and octal convert to binary for the computer. It's kind of like in this room, there might be, and all of us speak many languages, right? But the computer, even when we speak different languages, English, Chinese, Vietnamese, Spanish, right? It converts all of that to binary, no matter what. So these are just representation of value, but the computer has to convert everything to binary, right? The reason why we created these systems is this is how we use the system with processing. Different processor, you understand? Okay. And different type of use. So a 2, I cannot subtract 4, I put a 0. Okay. I go down the list. Can I take 2, subtract 2? Yes, right? I put a 1. So know that in an octal, it has 1 bit less than a decimal. 3 bits only. Okay, Dima? We got that? So 2 minus 2, I have nothing left. I put a 0. Okay. So this is how I get the value 2 is equal to 0, 1, 0. You're looking at me like, no, I don't get it. I'm sorry, say it again. Okay, this is just the position of the bits, right? It's kind of like first, second, and third. Okay? First bit, second bit, and third bit.
Is that a given?
Yeah, it's always like that. In a byte, right? The right one is always gonna be the first bit, the next one is the second bit, and the next one is the third bit. Now in an octal, it stops here. In a hexadecimal, it goes one more.
Right.
Right? And in a decimal, if you look at the representation of a byte, it goes all the way till the 8th bit. Okay? Like what we looked about decimal in IPv4 address, right? No, you don't have to memorize. What I'm trying to show you is if you know the scale, you can always convert it. It's kind of like translating it to another language that the computer speaks. Right? Okay. So I want you to practice, and so that way you can see, because if you don't practice and you just do rote memorization, that doesn't really apply the concept. Okay. So basically we're doing a little bit of computer math conversion, right? Okay. So I want you to go through and do C and B, right? So I did some of it, but I did not finish. I think I probably did. So the number 6, what adds up to be 6? The 2 and the 4, right? So I have 1, 1, 0. You ask yourself number 2, just like what we did. That's the 1, 0, 1, 0 from the last one. And the number 1, 0, 0, 1. So, and then as you do it, it gets easier. 3, 1, 2 adds up to be 3. So 0, 1, 1. 5, right? A 4 and a 1. So 1, 1 here. It gets really easy. And then the 4, just the first one is on, the last 2 is off. So if you want to use the table just to help out some of you that's new at this, right? So let's forget some of the answer here. Let's say that I want to use this table. You can just copy and paste this underneath here. And then clear this out and then go through each digit and you can check. What's a 6, right? I can subtract 4, so put a 1. I can subtract 2, put a 1, and then I put a 0. That gives me a 6. Okay. And then you can just reuse the table. So the table is really designed to show you, right, the bits position from the right to the left, and then the equivalents in decimal and the octal, the binary, as you go through and do the subtraction or the addition. Okay. I'm gonna try to get through. So we're gonna work on number 11, B, C, and then number 12, right? So for 12, the first digit is 4, right? You can put in the table, so that way you can see what a 4 looks like. So it should be 1, 0, 0. In binary, that's gonna be 4 plus 0, which is a 4 octal. Now, you can show your work as much as you want, right? I don't mind if you use the calculator, that's fine with me. But if you want to show that you understand, you can add in your work like you did the addition and the subtraction accordingly. So you have to solve these. Okay. All right, I gotta get through the rest over here, which is going back to the concept. So I'll pick up at 13 now. All right, we talked about concatenation with your address that has 0 in the block. So I put a link for your IP address representation. We talked about anytime that we have 0 blocks, right? Like the highlighted yellow here. And also 0 to start, right? Earlier, you heard there was a question that, well, there's only 3 digits in that block. Where's the 0? Sometimes some system would not include that 0 because it basically saying that there's a 0, but it doesn't count. So I highlighted some of the 0 in your addresses that's given to you. So it has 2026, 0CB0, etc., right? We're gonna condense it so that way it shows shorter in how some system would represent that address. So there are 3 versions of this. 1, you're gonna keep the first block, which is 2026, okay? And then you're gonna bring down the colon. Now the first 0 for the next block in green, we're gonna drop that, okay? It's not gonna care. So we're gonna omit the first 0 and we're gonna keep the C, the B, and the subsequent 0. Okay? Then the 2 blocks that have 0 in the middle there, we're gonna use the double colon to indicate that those are zeros following. You see that there? Okay. So I condense these 0 to a double colon right here. And then in following, I have another 0 to start, so I can drop that 0 and keep the F, the C, and the 0. So there's only 3 digits there. Okay. So FC0 comes down. Now I can still do a double colon for these guys over here, or I can do 0, colon 0, colon 0. So you can do it both ways. You can add a double colon where the yellow highlight is, or you can do colon 0, colon 0. It's 2 techniques, right? So I did another variation on Friday right here. All right. Yes. Yeah, on the same, that's correct. Yeah, you technically you can't have this, right? You have to indicate this like this and like this. So we have to keep it like that or like this. Thank you, Patricia. Then on the last one, we drop the front 0 here. We keep the A, the 2, and the E. So you can have a variation. You can keep the double colon on the front and then the 0 colon in the back because it has 2 blocks of 0 in between. You see? So yeah. So you're gonna see some addresses like this. You need to know what that means, right? So we can condense these guys into a double colon and then these guys into 0, colon 0, colon 0. Yeah.
With IPv6 addressing, what is more common to place the double 0 in a case like this? Would it be on the front set of 4 zeros or would it be on the back set of 4 zeros?
I see. So some system they only use colon 0. So yeah, you would see the double colon more often in the front. But
like in this case, since we have 2 places that we could put the double colon, what would be more common to see? Put it
in the
towards the front of the address. Okay.
So the way, but we can't condense it in both variations, like we can't have the double colon, so yeah, we would use the double colon and then the colon 0 subsequently. But you also have systems that uses the colon 0 in the front. So like I said, it also depends on the system. Right? Who manufactured that system and the programmer who created it.
But just, so be on the lookout for both.
Well, you just need to know what that means, right? The colon 0 means the block 0, and the double colon means 2 0 blocks. Okay, let's talk about the prefix. So, last week we talked a little bit about the CIDR, like 255.255.0.0 is a /16 or a CIDR 16. Similarly, we're going to use a slash to indicate the prefix for IPv6. So if you get a /4 like this, what does it really mean? Okay. First, you ask yourself, what is the length of IPv6? It's 128 bits. You take that 128 and you subtract the value that's given to you in the prefix right here, which is a 4. So you would take 128 minus 4, which gives you 124, correct? This 124 indicates that these are the number of hosts, right? This is going to be used in the exponent to calculate the number of hosts, which is the number of systems on that network, right? So this /4 right here indicate the network value, right? Whereas the remainder after you subtract, which is 124, that's going to be added to the exponent to calculate the number of hosts on that network. Okay, so we don't have to do subnetting too much with IPv6. We just have to know how to specify the number of networks and the number of hosts. So if you take this and put it into your scientific calculator, 2 to the exponent of 124, you're going to get the number of systems that you can connect. And you would see that that's a very large value. So this is what you would see with enterprise network, right? Network that requires many, many, many systems. Now, if you see a prefix 24, you take 128 minus 24, you would have 104, which is the value of n. And you would take 2 and raise it to the exponent of n, or 2 to the 104. That's going to give you the number of hosts for this prefix. Understand? So when you're asked, right, maybe you become a network engineer or you have to plan a network, right? Which prefix is going to give you this many computers? And the math is here. You would take the length of the address, right? And you subtract your plan prefix, like let's say I want to use /24, I would be able to calculate the number of hosts that I need to connect, right? Like every host requires an IP address. For example, like your sales terminal, your self-checkout terminal, etc., right? Inventory systems, printer. So this is going to give you the number of hosts for that prefix. And then you can continue to do C, take 64, subtract that from 128. And so let me write this out real quick so that way we are clear. Okay, and the same thing with 64. So prefix 64, you take 128 minus 64, you have 64. And 2 to the power of 64, that's going to be the number of hosts for prefix 64. So when you look at your IP configuration, look at IPv6 and the prefix, now you know what that means, right? It indicates the number of networks, and the remainder after you subtract, raise it to an exponent value base 2, that's going to give you the number of hosts on that network. Okay, almost done getting through. and then we will do our labs. Okay, so how can I have IP address without having conflict? In the past, IPv4, and you see this with network configuration today, when you're setting up your DHCP. Sometimes if we have the same IP address on the network, that causes disruption for those systems because you have to have unique host ID. So in IPv6, there is an auto configuration process that is built into the adapter. It automatically generates and look at the address that's already in use. And the way that it does that is it solicits the neighboring system. So if I have one computer that is getting ready to create an IP address, when it's in that process, it's going to check everybody else, right? It's kind of like saying, I'm gonna give myself a name, right? In the room, I'm gonna ask all of you to make sure that we don't have the same name, right? We have to be unique. So it's gonna solicit all the connected systems that's around it, and it's going to use the address, and it's going to say, hey, anybody using this address, or what is your IP address, right? And the other ones, it's gonna say, these are my IP address. So it's gonna check to make sure, and that's how it's gonna come up with a unique address. Okay, let me get to the portion where you see that. So auto configuration for IPv6, you can go to page 10 of 12. It's near the bottom of page 10. It talks about how it solicits the neighbor, right? To make sure that there's no duplicate of IP address. And then in the next section, it talks about IGMP. So in the next section, you're gonna see that there's ICMP version 6, and then also IGMP from version 4. So unlike the other protocols, when it was adapted into version 6, they decided that they would name it multi-pass listener discovery instead of IGMP version 6. So you would see this with DHCP version 6, ICMP version 6. But for IGMP, right, the replacement from version 4 into version 6, they name it multicast listener discovery. This is a way that it would handle communication to a group of systems by looking at the neighbors, right? Similar to, so the discovery processes to verify the status or the state of the system that's around it. So you got multipass listener discovery, or MLD. And then I think I mentioned the word tunnel when we talked about IP security. So in IP security, because it uses encryption, it creates a tunnel for the communication. So just think of it like it's a way to shield any kind of it uses encapsulation to shield any kind of intervention for that communication. So if you're using virtual private network, you don't want them to see your network activity, right? You don't want them to see how you're connecting to your network, which systems you're connecting to. So tunneling protocols work that way. It encapsulates and it shields that communication across using the headers, right? With encryption flags, so that way it would establish the communication securely. And in the next section, it talks about IPv6 tunneling. Right after you see all of these information about ICMP, like what I said, and the other protocol. So tunneling protocols is on page 11. And you would see that these are the terminology or the names of them. Okay. So Your 624 is for automatic tunneling. So let me close this so you can see the complete. These are for routers to determine the endpoints. So endpoints are systems that are not connecting to other systems spanning out, right? And then Torito are automatic tunneling protocols. These are also used for routers. And this use network address translation. So NAT is important, right? NAT is used to be able to translate your private IP into your public IP. At home, you might have 10 systems connecting to your router, right? All of those 10 systems, if you're gaming, if you're downloading, if you're streaming concurrently, it needs to leave your network and go to other networks. So your router handles the network address translation to take that traffic into the public network using the public IP. And so this is a way that your tunnel can be established with the routers, right, using NAT. Okay. And then subsequently, you would see some other protocol for tunneling, like ASATP along with Merito. So those are just a few. So, will you see this on network class? Yeah, there might be a question asked about tunneling protocols. You just have to memorize some of them, know to distinguish them, what they're used for, like Merito versus Torito. These are used by the routers for tunneling purposes, okay, for the service, and there are various services, right? Like Torito, so a Torito tunnel client, you can use that with Linux systems, and most Linux system implement 624 by default, but you can install Merito and Torito to support. So these are mostly used for Linux-based environment. So go to page 11 and 12. All right, let's go through some of the services real quick. These are review, and then we should be done after this. Okay. So if I have a Windows and a Linux system, I need to share files and printer. I need a service called Samba. Okay. So in your home network, if you have a mixed environment like this, in order to share one printer with the next, you need Samba. Okay, this is a service that you install right on your Linux machines, so that way you can share that the printer driver and the printer with your Windows system. This is a common environment in enterprise, because in infrastructure we tend to have like different servers that are in Linux and then Windows client systems maybe. You're gonna see wins when you are installing the HCP today. When you resolve and convert names into IP address, like system names, host names, this is gonna use WINS. So by default, Windows system will, the server or the OS, when you install the rule for the server, it's gonna ask you if you want to install this with it. Legacy wise, we do it for the purpose that some system might not have IP address, so we would keep it, right? You need to translate private to public IP. I just talked about this. This is network address translation, and you see this on your virtual machine as well. It uses NAT to be able to convert that into your host traffic, so that way you can have network connection. And then if you want to plan, document, and manage all your subnets, this uses a service called IPAM or IPAM. And you can go to the last section of the notes. It talks about these services. And if you want to remotely connect Windows network to access files and applications, including your cloud instance on Azure, AWS, and everything else, right? It's going to be your remote desktop protocol or your RDP. This is particular to Microsoft only. So if I have my Windows laptop and I need to connect to my Windows virtual machine, on Azure or AWS, the instance that I would spin up on my cloud server, I would use RDP. Okay. And lastly, minimize the configuration for clients by broadcasting services on network to the client. This is known as the zero config. This is it's also in the name, right? So if you want to reduce the configuration by not broadcasting to the entire network to everybody that is connecting as client, you would use zero config. Are we okay? Any questions? So I have a virtual machine that I zipped. It actually has the new server 2022 OS data center evaluation copy. For today, because of the time restriction, we are going to use the virtual machine. So before we start break and take attendance and before we begin lab, some of you started your lab. Before you start your virtual machine, make sure you give it 8 gig of RAM and 4 core, if not more. Okay. Your Alienware, the way you're sitting, has 16 core and 32 gig of RAM. So give it 8,000 megabyte, and the processor should be 4. Okay. Otherwise, you're gonna see that it's gonna be very laggy. So it's gonna take like 10 minutes to even load the desktop because the server environment is different. When you shut down your virtual machine, you gotta tell it why, because server, we don't shut it down. Okay. I did modify some things in the steps. The highlighted steps you don't have to do on your instructions. But I will go through with you on how to spin up your virtual machine from your drive. And then from here on out, I'm gonna try to put my virtual machine zip on my Google Drive and link it to your Canvas so that way you can just download, extract, and be able to use it. And if you miss class, you don't have to worry about that. So I'll work on that. It's just going into Google Drive with a compressed file that's that large, it's not exactly that fast. So it takes a little bit to upload and get it shared out. So I'll work on that tonight. And then as soon as I have it, I will link it to your lab page in case. But keep in mind that 2022 is slightly different than 2019. They are very close, but some stuff Microsoft add and some stuff they redo. So you can follow for most part. So I trained on 2000 and I can zip through 2022 easily, right? I certified in 2000, but anyways, so you should be able to use 2022 version. The ones on the drive is 2019. Most companies are still on 2019 as they haven't fully upgraded. Because when you upgrade server OS, just like how you upgrade in Windows 11, you gotta reinstall a lot of things, right? And when you do that, disrupt services, and that's not okay. So if we're finished with this, make sure you submit. I'll try to get your grades updated. I know I'm slightly behind in a couple of classes. I didn't get a chance to do yours from last week today. But I will try to catch up tomorrow and throughout the week. I will not be on campus on Thursday and Friday. I have to attend a meeting in San Diego for SM, but I will be back for next week. So yes, we will have class on Monday, unfortunately, right? Yes, fortunately we're gonna have class. But we are gonna do Windows Utility next week, and we are gonna use Windows Virtual Machine so you can configure and do some of that. And then I will turn on your module and try to upload your video stuff further. So we have a quiz next week. There's gonna be a quiz review game that's gonna be turned on throughout the week for Amazon gift cards. So if you participate, you get a chance to win. And then I'll let you know if you win. Okay. All right, let's stop recording.